In this first video, I want to introduce the new model for testing, an idea I brought in about a year ago to describe how we think about testing. Now, if you think carefully about what testing is, it's mostly a thinking activity. That is, if you remove all logistical stuff that clutters our thinking, what you're left is a pure test process. Now, before we understand test modeling, what I want to do is try and introduce this idea of the underlying thought processes of testing and modeling in general. Now, one of the things that becomes apparent is it seems clear that the thought process of testers and developers who are testing is pretty much the same. Now, what I want to do is to try and suggest that you clear your mind and forget what I will call logistics. That is, all the stuff to do with documentation and whether you're using tools or manual testing, what technology, what business you're in. These are all logistical challenges. So let's take all those away and free your mind and let you think more clearly about testing. I want to talk about models in general and suggest that they're essential to human existence. You know, our brains are fantastic modeling engines. I'll show you the new model and introduce it in stages so you have a good understanding of where I'm coming from and how you might think about testing. And then I'll talk in more general terms about how the new model fits the development process and summarize at the end. Now, my thesis in thinking about whether the model is required is that because we have such pressures we've never had before, we have digital, continuous delivery, DevOps, shift left, analytics coming in more and more. I want to suggest that the old ways of thinking about testing won't work in the future, certainly won't work as well, and they have to change. So my suggestion is we need a new model of testing free from logistics, free from the complications of the process we follow. So I want you to clear your mind, forget logistics. So I'll put it this way. I don't care, and you should not care, whether you document your tests or not. I don't care whether you use a tool to run your tests or you run them by hand, or you run some other piece of magic to exercise, to run your tests. I don't care whether you use an Agile process or a waterfall or a structured process or your continuous or DevOps or whatever. I don't care. I don't care what business you're in, whether you're in banking or insurance or telecoms or health or government. It doesn't matter. I don't care what technology you use, whether you're building websites or mobile apps or you're working on mainframes. I don't care. It doesn't matter for the purpose of understanding testing. So let me start from the beginning with a statement that all testing is exploratory, and let me walk you through the mission, if you like, of what I think is testing. We explore sources of knowledge. Our sources of knowledge could be requirements documents, interviews with people, standing up as a team in front of a whiteboard. It could be standards and conventions and design heuristics. It's also what's in our head, our experience and our knowledge and our biases and misunderstandings as well. These are our sources. We explore our sources. And in order to make sense of our sources of knowledge, we build mental models. I'll call them test models, but they're just models. Now, in the next slides, I'm going to suggest that what we do with models is they help us to understand. And you could substitute the word understanding everywhere in this presentation where the word model is used. When we think we understand, when we think our model, our mental model or our documented model is accurate enough to proceed, we then use that model to inform our testing. So we explore sources of knowledge to build mental models that inform our testing. Let me just illustrate this idea of models with a few examples. Here's a Gantt chart from Microsoft Project, I'm sure you're familiar with and love or hate. It's a description of how the activities of a project can be synchronized in order to deliver some product or achieve some goal. Now, everyone in the project has a role in a project. The Gantt chart tells you what your role is, where it happens, when you have to start and when you have to end, perhaps. For project managers, it's their kind of Bible. For project managers, it's their reality, even though a project plan is a model of the future. Here's a sequence diagram, an example of a UML model. You have actors along the top, librarians, books, member records, and so on. And what the sequence diagram tells you is the sequence of activities in collaboration and in sequence that allow you to meet some goal, to update a member record in this case. Here's another UML model. It's a class diagram, handwritten, but still a model. Each box has an object definition. It contains data plus features or functions. Each class itself, each object, is connected by relationships with cardinalities in terms of numbers of relationships, one to many, and so on. It's a model of the objects in a system. Here's a weather map, a weather forecast. A weather forecast is the output from a system model running on a supercomputer. The model has data from all over the planet fed into it. This data might comprise temperature readings, wind speed, direction, humidity, barometric pressure, and so on. The supercomputer takes the model and crunches the numbers to generate this forecast, which is wrong. This phrase, all models are wrong, some are useful, was derived by an economist, George Box, talking about economic models. But it's generally true. All models are wrong, some are useful. Although the weather forecast we know is not perfect, it is still helpful to plan journeys, to make decisions about what we do in the open air, if you like. Here's a piece of mathematical physics, Nobel Prize winning mathematical physics. It's actually the equation of the electron behaving as a wave from Paul Dirac. Now, what use is this piece of mathematics, this piece of physics to testers? Well, none, except I want to illustrate the fact that this piece of mathematics is a model of some aspect of nature. It's wrong, but it's useful. It can be used to make predictions. Here's another model, which is the London Underground or tube map. Now, the tube map itself is clearly not geographically accurate. The dimensions and the relations and the distances between the stations on the diagram is not to scale. It's all over the place, you might say. But it's useful in that it shows the relationships between stations and the paths we can take on the tube network in order to get from one station to another. The model is wrong, but it's very useful. So all this talk of models, I just want to summarize it by suggesting that the way that the brain works is remarkable in that it is using models all the time. Suppose you are this chap here and you're thirsty and there's a glass of water a few steps away on a table. In order to take a single step, your brain has to understand the configuration of many bones in your body, all the major limbs, of course. It has to understand the tensions in all the muscles, the 100 or so muscles required in order to take a single step. And when you decide to take a step, your brain has to send a whole series of nerve impulses in synchrony to all these 100 muscles. Now, in order to do this second by second and even faster than that, your brain has to process vast quantities of data. Except it's not possible to process vast quantities of data in your brain. It's organic rather than a digital computer. What your brain does clearly is build some extremely sophisticated models of the configuration of the bones and the muscles that connect them, and it makes decisions on the basis of the outcome of this model rather than the reality of all the nerve impulses and electrical signals, the muscles and the flesh and blood and the bones and everything else. It must use some simplification because the brain is simply not powerful enough to process data fast enough. So your brain is a fantastic modelling engine. And in testing, everything we do is associated with a model, usually a mental model that might never be written down. So in software development, requirements, user stories, specifications, sketches on a whiteboard can all be models of a system from the perspective of a user, perhaps. Architecture diagrams, flowcharts, sequence diagrams, process flows, state diagrams. These are all models from the perspective of the user, the developer, or maybe even the tester. Testers can use any of these models or even invent their own to deal with unusual circumstances or specific modes of failure, or to represent the system under test in general. Now, the user or developer might think one model is enough, one set of requirements is enough, but testers often have to use multiple models to focus on different aspects of a system to test it thoroughly. Now, if you think back to the traditional test design techniques, equivalence classes, boundary values, decision tables, state transition models, these are all models. They're all based on models. The techniques are simply the model interpreted. Risk registers, failure modes, bug patterns, checklists, these are all models too. They may be more or less sophisticated, but these all help us to understand our system or the modes of failure of our system so we can derive tests in a meaningful way. The strapline I introduced a bit earlier, we explore sources of knowledge to build test models that inform our testing. This is our mission statement for testing, if you like. Let me just walk you through at the highest level how we think about testing. When we start the test process, we explore our sources of knowledge, whether it's requirements, designs, we interview people, stories, our own knowledge and experience, the existing system, the old system. These are all sources. We explore these sources, and in order to understand what we see and what we hear, we make models. Our models represent our understanding. They allow us to make sense of a very complex set of requirements. Now, when we believe our model is okay, we trust it. We trust that it's ready for us to test. We use the model to inform our testing, and we conduct our testing on the system under test. Now, what can occur very often is once we start testing, we start learning new facts, new information about the system. And it might be, and it's common, that we realise our models are not adequate. Our understanding is not perfect. We have to go back to explore further, to ask questions of our users to get to the bottom of some anomaly that we discover. Now, at the heart of all this is this green blob called judgment. Now, I can't tell you what's inside this green blob, except the green blob judgment must exist. We use judgment to decide whether our models are adequate or our models are not adequate. Now, the hope is that we don't have to go through this loop too many times. We start on the left, but we want to be on the right. The question arises fairly quickly, do developers explore the same way? Now, my answer is I believe so. And the reason for this is that when they start from the point of view of a set of requirements or their own sources of knowledge, which typically are the same sources for developers and testers, they have to create their own mental models. Their goal is slightly different, to build software, to write code, but it is also to test. So the models they use to develop their software are the same models they use to think about testing. So I think developers explore in a very similar way on the left-hand side, and the way they test, because of the nature of testing, they might work at a lower level, at a code level or a unit or a module level, but the way they arrive at their test designs, I believe, is fairly similar to the way that a tester designs their tests at a system or an acceptance level. Now, I'd want to go through the left-hand side and the right-hand side of that picture in a bit more detail, and then I'll glue it all together in a moment. The exploration process takes our sources of knowledge, system under test, requirements, people, our own knowledge. We ask questions, we inquire, and this is what exploration is really about, asking questions. As we gather information, we make models in order to assimilate the knowledge we gain, and we build models. Now, when we have a model that we trust, we can use that model to make predictions. And when we make predictions, we might find anomalies in our understanding, at which point we can take those anomalies and, using examples worked through the model, worked through the requirements, we can challenge our sources to get to the bottom of things that don't look right, if you like. So we have on this left-hand side of the new model, the whole thing, We have inquiring, modelling, predicting, challenging. We have these feedback loops, predicting and challenging, which help us to clarify requirements, to get our model accurate and to be in a trusted state to proceed further. When we trust our models, we can move to the right. We have our test model. That test model can be used to inform our testing. Now that model could be something as mundane as a flowchart or a state model or a checklist. It doesn't matter. These are all models. The model informs our testing. Then we apply our test. Applying could be running using some test automation technology, or it could be doing it manually, or it could be using some other form of magic. It doesn't really matter. That's logistics. We apply the tests. We check whether there's a pass or fail, it meets a requirement or matches an expected result, yes or no. Now, having got those results, we then interpret those results. We might run 100 tests and then look at the pattern of successes and failure to interpret and to make a decision, a choice of what we do next. Now, one thing we might do is log a bug, a failure, if you like, where we revise the system and feed that into the system under test again and go through the applying, interpreting loop again. It may be that we report the outcome of all our tests, and that's a natural thing for all testers to do, to share what they do. We test on behalf of other people, most of all. Sometimes we discover that our understanding is not perfect and we have to go back to our model and refine it in some way. Sometimes we have to go right back to the beginning and go back to our users and ask questions of them and ask, is this the way the system should work? Yes or no? Quite often they will tell us, you've found an anomaly in the requirement, we need to do some more thinking, or it might be there's an anomaly to do with an ambiguity, or there's a gap in the requirement in the first place. At any rate, more exploring quite often is the path we have to take back to the start. When you glue the left and the right hand sides together, you get this kind of picture. Now, the intent wasn't to come up with a picture that looks like a bug, although that's what it ended up looking like. It's just happenstance that that's the way it's turned out. But you can see that it describes the process of thinking from the testing perspective, right from the source of knowledge through to the application of tests and the reporting of those outcomes at the end. You can see a bit more detail, a video and also a longer paper describing the model in detail at the newmodeltesting.com website. Now, I want to talk about the model and the development process in a little bit more detail, just to draw some conclusions about how it can be useful. If I use my PowerPoint skills to move things around, I have two versions of the model. You can see if I strip away all the feedback loops, just to simplify the model, we have the developer's journey and the tester's journey. The tester's journey we've just talked about. If you look at the corresponding developer's journey, it's the same until it comes after the informing stage, where the developer's goal is to design, to code, and to test some software. So they have an applying testing phase, just like the tester does, and the system under test is the component at whatever level of granularity they're working at. So I want to suggest that the developer's journey and the tester's journey are very similar. The thinking they go through is the same in its pattern. The thinking is different. The models might be different. Now, the new model suggests that the thought processes of developers and testers, the people who design and build the software and the people who test that software, the thought processes are the same. The thinking is different, but the processes are the same or very similar. So because collaboration between developers, testers, and users or product owners, this is a common working pattern now, the new model for testing could suggest how each of the participants in the project is actually thinking day to day. So where you have some kind of conflict, it often is the case that the thinking of the tester might be, we've not got the requirements right yet, might be different from the developer who says, well, my tests are not passing because it's not clear what the outcomes should be. The thinking and the stages of thinking, the maturity of the thinking almost, might be different within the team. So the model might help you to resolve some conflicts. Certainly the model could form the basis of a shared understanding and collaboration. It's not a process with inputs and outputs and a procedure. It just shows you the stages of thinking that your brain can be in when you think about testing. I have to suggest that our brains might be so sophisticated that on the basis of several requirements, we are at different stages in our thinking simultaneously. I think our brains can actually do some of these things in parallel on different requirements. Now, models are the language of requirements, design and test. There's nothing I've said in the last few minutes that is new or revolutionary. All I've done is propose a picture that describes the states of our brains, of our testing at various stages, and the sequencing of those stages of thinking. So software engineers, software people in general, follow a long line of other engineering disciplines who use models to support collaboration and design. In the context of software, models are used to represent requirements, they assist collaborative design of the product, and they assist collaborative design of the tests of that product. Now, the models used by developers and testers do not have to be the same. They might be the same, but they don't have to be. In fact, independent testers might come up with completely different models of their understanding of how a system should work. And that's a benefit of independence, if you like. But the models they create must be consistent with the models of the developers. If there's a difference in understanding, there's a problem in your project. So essentially, testers, it can help if your models differ, but they should be consistent with what goes before.